Hello, welcome back. Now we'll start coordination compounds. Before starting of the coordination compound, let us know about coordinate bond. Coordinate bond is otherwise known as dative bond. It is denoted by an arrow. Suppose NH3 is there. NH3 is a neutral compound. N has a lone pair. Another H plus is there having no electrons. So this pair of electrons can be donated by this nitrogen to this H plus and shared by both N and H plus, and it forms NH4 plus. So here between N and H there is a coordinate bond, or you can say a dative bond. So in coordination compounds you'll find bonds like coordinate bonds between central metal atom or ion with ligands. Let us take an example. CuNH3 4 2 plus. You see this Cu is Cu2 plus. Oxidation number of Cu is x plus 4 into 0 is equal to plus 2, and x is found to be plus 2. So this 2 plus is the charge on copper 2 plus. 2 plus is the charge on copper. It has vacant d orbitals, and you see each n has a pair of electrons on nitrogen atom. So this lone pair can be given to this Cu2 plus to form a coordinate compound, and this 2 plus can be written over here. You see Cu has vacant d orbital. The lone pair on nitrogen can be donated to the central atom. Here copper is a transition metal ion. Here copper is a transition metal and Cu2 plus is a transition metal ion. Ammonia is a ligand, and N over here is a donor atom having a pair of electron, and these are coordinate or dative bonds. These are in the previous unit we have learned that transition metals form a large number of complex compounds in which the metal atoms are bound to a number of anions or neutral molecules. Here the metal atoms or ions bound to a number of anions like Cn minus, Cl minus, F minus, etc., or neutral molecules. You see ammonia is a neutral molecule like ammonia, water, etc. For example, FeCN6 4 minus. Here Cn minus is a ligand, Fe is a metal atom Fe is present here as Fe2 plus metal atom ion. Cn minus is a ligand. In modern terminology, these compounds are called coordination compounds. Coordination compounds. There are three types of coordination compounds: cationic, anionic, and neutral complex. Cationic means positive charge on the cation, like Cu NH3 whole 4 2 plus. Anionic means FeCN6 3 minus. This is anionic. Neutral means no charge on the complex, zero charge. So this is a neutral complex, this is an anionic complex, this is a cationic. Some vital components of biological system. Example, chlorophyll is a complex compound of or coordination compound of magnesium. Then hemoglobin is a complex compound of iron. Vitamin 12 is a complex compound of cobalt. Variety of metallurgical process, industrial catalyst, and analytical reagents involve the use of complex compounds or coordination compounds. Coordination compound has application in electroplating, textile, dyeing, and medicinal chemistry. Then we'll start Werner's theory of coordination compounds. Werner's theory of coordination compounds. Alfred Werner. Swiss chemist. He was the first scientist to formulate about the structures of coordination compounds. He prepared and characterized a large number of such compounds and studied their physical and chemical behavior by simple experimental methods or techniques. Werner proposed the concept of primary valence. He introduced two types of valence: primary valence and another one is secondary valence for a metal ion. Two types of valency for metal ion. You see, in CrCl3, primary valence of Cr3 plus is 3. ClCl3 primary valency of cobalt is 3. In PdCl2, primary valency of PD is equal to 2. And secondary valency, suppose Cl3 6 ammonia. Here secondary valency of cobalt is 6. And these are binary compounds. Binary means two types of elements are there. Next, he took COCl3 6 ammonia. Here primary valency of cobalt is 3. Secondary valency of cobalt is equal to 6. He took 1 mole of COCl3 dot 6 ammonia. It is a yellow color complex compound treated with silver nitrate. Sufficient large amount of silver nitrate, or you can say excess silver nitrate, and produces, and here you have taken 1 mole of COCl3 6 ammonia. With excess silver nitrate produces 3 moles of AgCl. Means these 3 chlorine atoms present in COCl3 as chloride ion can be precipitated as AgCl. As you have taken 1 mole, there are 3 moles of chlorine atoms in COCl3. So in large amount or excess amount of silver nitrate, it produces 3 moles of AgCl. If we will take 1 mole of COCl3 5 ammonia, it is purple in color, with excess amount of silver nitrate, it produces 2 moles of AgCl. It is interesting. Why does this compound give 3 moles and why does this one gives 2 moles? Let us explain. Secondary valency of cobalt is 6. That is coordination number. It is fixed. Primary valency of cobalt is equal to 3. That is ionizable. This structure can be written like this. You see CO at the center and its secondary valency is 6. So let us draw 6 solid lines. Six ammonia molecules. These 6 ammonia molecules will form bonds with central atom cobalt, and another Cl, 3 Cl atoms will form primary valency by dotted lines. These are primary valency, these are secondary valency. Secondary valency are denoted by solid lines and primary valency are shown by dotted lines. This compound, according to modern theory, can be written CONH3 6 Cl3. You see, this is according to modern theory. This is not according to Werner's theory, When this molecule is treated with excess silver nitrate, you have taken 1 mole of this complex, and with excess silver nitrate, these 3 chloride ions present outside the coordination sphere. This is your coordination sphere, and these are counter ions. these three counter ions will be treated with silver nitrate to produce AgCl. As you have taken 1 mole 1 mole of this complex compound with excess silver nitrate, you will get 3 moles of AgCl. Means all these counter ions present outside the coordination sphere get get precipitated as AgCl. But in case of COCl3 5 ammonia, what happens? This is COCl3. Let me write again, COCl3 5 ammonia. You know secondary valency of cobalt is 6, that is fixed, and primary valency is equal to 3. So we have to draw 6 solid lines. Why? Because secondary valency of cobalt is 6 is fixed. But here there are 5 ammonia molecules. Let us write 5 ammonia molecules. And 3 chloride ions are there. Another solid line is there without having any ammonia molecules. So we should write dotted line over here. That means chlorine here forms a coordinate bond with central metal atom. And this compound in modern theory can be written in a different style. You see, CO, there are 5 ammonia molecules, so CONS3 5, but its secondary valence is 6. Here there are 5 ammonia molecules, so another chlorine forms a coordinate bond with central cobalt, and these 5 plus 1 6 ligands are kept in the square bracket, and another 2 chlorine atoms are written outside the coordination sphere as counter ions. When we will take this complex CONS3 5 Cl2 with excess silver nitrate, let us take this one as 1 mole, then obviously we will get 2 moles of AgCl. 2 moles of AgCl. Here Werner proposed the term secondary valency for the number of groups bound directly to the metal ion. In above complex compounds, the secondary valency of cobalt is 6. That is fixed for cobalt, but in some cases you will find 2 or more secondary valency for a single metal ion. Usually it is fixed, but in some cases you will find more than 2 or 3 secondary valency for a single metal ion. In COCl3 4 ammonia, you will find 2 types of compounds having identical molecular formula. One of them is green in color and the other one is violet in color. Here the structure is COCl2 4 ammonia, and another chlorine is outside the coordination sphere. Cl2 4 ammonia and another chlorine is outside the coordination sphere. Here you see this compound can be written like this also: CO NH3 whole 4 Cl2 Cl. It is also written like this: CONH3 whole 4 Cl2 Cl. But interesting, one of them is green in color and the other one is violet in color. So these two compounds are isomers as they have same molecular formula. So definitely here we'll discuss in detail when we'll discuss isomerism of coordination compounds. You can guess what is the difference between these two isomers. Postulates of Werner's coordination theory. Postulate number 1. In coordination compounds, metals show primary valence and secondary valency, two types of valences. Number 2, primary valency, or you can say primary valences, are ionizable. Secondary valences are non-ionizable. Primary valency or primary valences are satisfied by negative ions. You see COCl3, this is a negative ion, and primary valency of cobalt is equal to 3, satisfied by negative ions. Secondary valences are non-ionizable, satisfied by secondary valences are satisfied by neutral molecules, example ammonia, or negative ions like Cl minus, F minus, Cn minus, etc. Secondary valence is equal to coordination number. Secondary valence is equal to coordination. Secondary valency is equal to coordination number. Secondary valency is equal to coordination number, and it is fixed for a metal, atom or ion. But sometimes you will find more than 2 types of secondary valences for a single metal, atom or ion. We will discuss later. Next, the ions or groups bound by secondary linkage to the metal have characteristic partial arrangements corresponding to different secondary valency or coordination numbers. The ions or groups bound by secondary valency or secondary linkages to the metal have characteristic spatial arrangements corresponding to different coordination number. Such spatial arrangements are called coordination polyhedra. Spatial means in space, the arrangement is in space. The complex compound or ion within square bracket, the complex compound ion within square bracket is the complex compound or ion, or you can say the species within square bracket the complex compounds or ions, the complex compounds or ions within square bracket the complex compounds or ions, or you can say species within square bracket are coordination entities or complexes. The ions outside the square bracket are called counter ions. Suppose CO NH3 whole 4, this is the coordination number, this is the central metal ion, this is the ligand. He further postulated that octahedral, tetrahedral and square pyramidal complex compounds are more common in coordination compounds. Octahedral, then tetrahedral, then square, planar, geometrical shapes are more common in complex compounds of transition metal ions or atoms. CO NH3 6 3 plus COCl CO NH3 5 Cl 2 plus Cl2 plus are octahedral entities, while NiCO4 PtCl4 2 minus are tetrahedral and square, planar respectively. Or you can say whereas NiCO4 is tetrahedral having sp3 hybridization. PtCl4 2 minus is square planar having dsp2 hybridization. This is square planar having dsp2 hybridization, and this is tetrahedral having sp3 hybridization. We'll discuss later. PtCl2 dot 2 ammonia with excess silver nitrate produces 0 mole of AgCl. Here you see this complex compound is treated with excess silver nitrate, and here we have taken 1 mole, not told, 1 mole of PtCl2 2 ammonia with excess silver nitrate produces 0 moles of AgCl. Then what is the secondary valency of the complex compound, this complex compound? You see PtCl2 dot PtCl2 dot 2 ammonia with excess silver nitrate produces 0 mole of AgCl, means no chlorine is present outside the square bracket. You won't find any chlorine atom outside the square bracket, so it should be inside the square bracket. PtNS3 whole 2. As there is no chlorine atom outside the coordination sphere with excess silver nitrate, it won't produce any AgCl or any precipitate of AgCl. So here secondary valency of Pt is definitely 2 plus 2 4. Secondary valency of Pt is 4, and the oxidation number of Pt in the above complex compound is plus 2. How? You see Ptx, oxidation number Pt is equal to x, let it be x. Ammonia, for ammonia it is 0 into 2. For chlorine it is minus 1 into 2 is equal to 0 because it is a neutral complex. So x plus 0 minus 2 is equal to 0, x is equal to plus 2. X is the oxidation number of platinum. Then we'll discuss about difference between double salt and a complex compound. You see KCl MgCl2 dot 6 water is a double salt. Which salt? Double salt. Why double salt? Because you will find 2 salts over here, so it is a double salt. When it is put in water, it gives the test for K plus, Cl minus, Mg2 plus. It gives the test for all ions. And this is known as kernelite. It gives the test for all ions, and it is a double salt because there are 2 salts over here. However, K4FeCN6 is a complex compound. In water it gives 4K plus FeCN6 4 minus, FeCN6 4 minus, and these FeCN6 4 minus do not give the test for Fe2 plus or test for Cn minus. So this is a complex compound. You see in the double salt, it gives the test for all ions, but here it doesn't give the test for Fe2 plus or Cn minus ions. Now we will discuss some terms in coordination compounds. Coordination entity. Coordination entity. It constitutes a central metal atom or ion. Example, NiCO4. Nickel is the central metal atom. FeCN6 4 minus. It contains Fe2 plus, central metal ion. Here you see nickel is surrounded by 4 carbon monoxide molecules, and this is the coordination entity. Next, central metal atom or ion. You see in CO NH3 Cl2 plus the central metal ion is CO3 plus. It is surrounded by 4 ammonia molecules and 2 chloride ions to form an octahedral complex. Here cobalt is surrounded by cobalt 3 plus is surrounded by 4 ammonia molecules and 2 chloride ions to form an octahedral complex. Octahedral complex. In modern theory, it can be written as CO3 plus central metal atom or ion are known as Lewis acids. Lewis acids. Then ligands. The ions or neutral molecules bound to central atom or ion in the coordination entity. This is a coordination entity. In the coordination entity, this is also a coordination entity, are called ligands. So in NiCO, these CO molecules are ligands. These CO molecules are ligands. Examples of ligands: Cl minus, Cn minus, H minus, F minus, Br minus, etc. or ammonia, water, etc. These are neutral molecules, these are ions. Some larger molecules can be treated as ligands, like ethane 1,2-diamine. You see ethane, and it has two NH2 groups. This is 1,2 ethane 1,2-diamine. So it is a bigger molecule, and it is also treated as a ligand, but this is a bidentate ligand because it can form two coordinate bonds with central metal atom or ion. You see, in Cu2 plus this CH2 will form two coordinate bonds. Form two coordinate bonds. This is a bigger molecule, or you can say ligand. It is also written as En, and this is ethane 1,2-diamine. Even macromolecules like protein is also treated as a ligand. When a ligand is bound to a metal ion through a single donor atom, it is known as unidentate. Suppose Cl minus, it forms one coordinate bond. It forms one coordinate bond with central metal atom or ion. It is unidentate. Ammonia, this lone pair forms a single coordinate bond with central metal atom or ion. So it is a unidentate ligand. And the above one, En, is a bidentate ligand. Why? Because it forms two coordinate bonds with central metal atom. Oxalate ion, CO minus, it can form two coordinate bonds with central metal atom, so it is a bidentate ligand. Bi means two, dentate means it can form bonding with the central metal atom or ion. And this is your oxalate ion, OX. Or you can say didentate. In your book it is written didentate, so no need of writing bidentate. Didentate, oxalate. Then EDTA, it is a hexadentate ligand. You see the structure of hexadentate ligand. You know this is CH2, ethane. It has two NH2 groups, so it is ethane 1,2-diamine, just written over here. This is ethane 1,2-diamine. If we will remove these two H atoms and substitute CH2COO minus, then you should remove these two H atoms from here also, and we can substitute CH2C11O minus, same thing over here, CH2C11O minus. and you know nitrogen contains a pair of electrons as lone pairs. So you see it is also hexadentate. Why? Because here O minus is there, O minus is there, lone pair is there, one lone pair, here another lone pair is there, minus charge, minus charge. So 4 minus charge plus 2 lone pair, total 6. So it is hexadentate. Hexadentate. And the name is ethane 1 2 ethane 1 2 diamine, because 2 nitrogen atoms are there. Then these are acetate, and how many state parts are there? 4. So we can write tetraacetate. We can write tetraacetate, and the name is EDTA. It is hexadentate. EDTA 4 minus. EDTA 4 minus. Why? 4 negative charges are there. It can bind through 4 oxygen and 2 nitrogen atoms. It can bind through 4 oxygen and 2 nitrogen atoms. It can bind through 2 nitrogen and 4 oxygen atoms. Then chelate ligand. Chelate ligand. You see, chelate means a ring structure. Cu2 plus, you see ethane 1 2 diamine forms a chelate. Chelate means ring structure. Ring structure. Chelate means ring structure. So this is a chelating ligand. Chelating ligands form more stable complex compounds. You see in CuNH3 4 2 plus, here coordination number of copper is 4, and in CuEn, this part is known as En 2. Why? 2 ENs are there, 2 plus, and here the coordination number of Cu2 plus is 2, as it is bidentate, is equal to 4. So in both cases coordination number is same, but it is more stable. It is more stable because of chelating ligands, because of chelate formation. Then denticity. The number of such ligating groups, is called denticity. The number of such ligating groups is called denticity of ligand. In case of ammonia, the denticity is 1. In case of Cl1, the denticity is 1. In case of PN, the density is 2. In case of EDTA 4 minus, the density is 6. In case of EDTA 4 minus, the density is 6. Then ambident ligand. It is a monodentate ligand. It is a monodentate or unidentate ligand having two donor atoms. You see, example, NO2 minus. NO2 minus has two donor sides, either through oxygen or through nitrogen. It can connect it to the central metal atom through N, or it can connect through O. You see, here metal is connected to NO2 minus group through oxygen, and here it is connected through nitrogen. So it is a monodentate ligand having two donor atoms. Similarly, another example we can take SCN minus. It can connect through central atom like this, or it can connect through central atom and MSCN. If it is connected through S, so we can write thio for sulfur, thiocyanato. And this is connected through N, and this is the isomer of this one, so you should write isothiocyanato. And this one is nitrito. This is nitrite. This O is converted to O, nitrito. N. Why N? Connected through N. And this one is nitrite. Is converted to O, nitrito. Nitrito O. Thio means sulfur. Then coordination number. Coordination number of central metal atom or ions in a complex compound. Can be defined as the number of ligand donor atoms to which the metal is directly bonded. Coordination number of PT in PtCl6 2 minus is 6, because 6 chloride ions or ligands bonded to central PT. So coordination of PT is equal to 6. In Ni NH3 2 plus, the coordination number of nickel is equal to 4. Here you see ammonia and Cl minus are unidentate ligands. So number of unidentate ligands is equal to coordination number. But in case of Fe C2O4 3 minus, here it is a bidentate ligand, or you can say didentate, So 2 and number was 3, so total 6. So the coordination number of Fe is 6. C2O4 is written like this. It has 2 atoms bonded to central metal ion, Fe3 plus, you can say. In CO, En3 3 plus, coordination number of CO3 plus, or you can say CO, is equal to 6. Why? En is a didentate ligand, means 2, and number of En molecules are 3, so 2 3s are 6. So coordination number of cobalt in this complex is 6. It is important to note that coordination number of central metal atom or ion is determined only by number of sigma bonds found by the ligands with the central ion or atom. Pi bonds if found between the ligand and the central ion or atom are not counted for the purpose. So coordination number is due to sigma bonds only, not due to pi bonds. So coordination number of central metal atom or ion is due to sigma bonds only, not due to pi bonds. Then coordination sphere, not due to pi bonds. Then coordination sphere, central atom or ion and the ligands attached to it are enclosed in square bracket, enclosed in square bracket, enclosed in square bracket is termed as coordination sphere. You see, NiCO4 in the square bracket is known as coordination sphere. CuNH3 whole 4 SO4 2 minus. This is your counter ion. Ionizable groups are written outside square bracket are called counter ions. Example, in K4 FeCN6 counter ions are K plus ions. Then coordination coordination polyhedron. Polyhedron, plural is polyhedra. This is the spatial arrangement. Spatial means 3 dimensions, space. The spatial arrangement. This is the spatial arrangement of the ligand atoms which are directly attached to the central atom or ion. This is the spatial arrangement of the ligand atoms which are directly attached to the central atom or ion. Defines the coordination polyhedron about the central metal atom or ion. Coordination polyhedron, plural polyhedra. You see, if the metal atom is over here and the ligands are written like this, these two are on paper. This is tetrahedral. This is tetrahedral. Here I have written polyhedron. Poly means many. Instead of poly, I have written tetra. Polyhedron. Here it is tetrahedral. Bonded to 4 ligands on 4 different sides. And here most probably the hybridization of metal atom will be sp3. Then you see similarly 4 ligands and bonded to the central atom in this fashion, and this is square planar, and here the hybridization of central metal atom is dsp2. Then you see here metal atom is there, just you have made a square planar, then above it ligands are there. These are monodental ligands. This is octahedral. We can draw like this also. You see, this one is towards U. This was it will form a plane, and this is above the plane, and this is octahedral. Then you see metal atom is there, ligand, a plane is made over here, trigonal plane, above it L. This is trigonal bipyramidal. This is trigonal bipyramidal, because above this plane, trigonal plane, you can make a pyramid, and at the bottom you will also find a pyramid. So this is trigonal bipyramidal. Another structure is there, square pyramidal. Square pyramid means this is metal atom, two ligands. These two ligands are towards U, and above the plane you will find a square pyramidal. Square pyramidal. So these are polyhedrons. These are polyhedra. Polyhedra means tetrahedral, octahedral, square, planar. Then oxidation number of central metal ion, of central metal atom. Suppose AgNH3 whole 2 plus is there. What is the oxidation number of silver? Let it be X. For ammonia it is 0, as there are 2 ammonia molecules into 2 is equal to plus 1. So X plus 0 is equal to plus 1, X is equal to plus 1. AgCN2 minus. Here X for Cn it is minus 1 into 2 is equal to minus 1, X is equal to 2 minus 1 is equal to plus 1. Oxidation number of Fe in FeCN6 3 minus is X, for cyanide it is minus 1 into 6 is equal to minus 3, X minus 6 is equal to minus 3, and X is equal to 6 minus 3 is equal to plus 3. So the oxidation number of Fe in this complex compound is plus 3. Oxidation number of Fe in this complex ion is plus 3, and it is written as Fe Roman letter 3. This is upper Roman numeral, upper Roman numeral. Plus 3 is written as Roman letter, upper Roman numeral. Then homoleptic complex compound. In homolytic complex, the central metal atom or ion is bound or linked to only one kind of donor groups, and you know donor groups are ligands. Example, CO NH3 whole 6 3 plus. Here you see ammonia is one type of ligand or one donor group, so there are 6 donor groups, so it is homoleptic. Homo means same type of ligands are there. Then heteroleptic, heteroleptic complex compounds or ions. In heteroleptic complexes, the central metal atom or ion is bound to more than one kind of donor groups. Example, CO NH3 Cl2 plus is heteroleptic. Why? Two types of ligands are there. Here donor group is ammonia and chloride ions. So it is heteroleptic. Hetero means different. In above example you see one type of donor groups. Thank you. In the next part we will start nomenclature if time and tide permit.